wanted to give you a little bit of background on the circular functions investigation because if you get off on the wrong track, you basically will spend a whole bunch of time doing the wrong thing and just frustrating yourself. So the idea here is we're looking at relationships that happen when circular motion occurs and angle measures and different things like that. So if you remember, Joaquin is out socially distancing, riding his bike. Okay, he rolls over some paint and we pick up, he notices this paint spot, basically when it's located right here. We're going to look at its motion. We're going to superimpose it onto a coordinate plane to be able to see some different relationships here. So the hub of his bike is basically going to be at the origin, hub of his tire, and everything's kind of happening around that. So the paint spot is going to start out right here. Notice if we were graphing in standard position, that's starting out at a 0-degree angle. We are thinking about his bike tire moving counterclockwise, okay? It's going to be moving like this. And so, you know, the big idea here is basically we can see some patterns as that tire continues to rotate, okay? Now, a couple of things. His bike tire has a diameter of 24, I think, inches, so the radius is 12, and that's super, super, super important. Okay, so what I'm going to have you graph here is the relationship between the angle measure that his tire has rotated through, starting at a 0-degree angle, and we're going to be looking at the height of that paint speck, not above the ground, but above center. In other words, what's the height of this above the x-axis? Okay, so we have basically our x-axis is going to be the angle measure, okay, and the y-axis is going to be distance above the x-axis, okay? In other words, how high that point is, okay? So we're going to need to find some coordinates as this moves around. However, the circle's symmetrical, so you're going to see a lot of things that kind of continue to be the same. So at a 0-degree angle here, he first notices this paint speck. The paint speck is lying on the x-axis when we superimpose this into a coordinate plane. So that's the point 12, 0. We're really looking at the y-coordinate of the point there. So at a 0-degree angle, the height of that is 0 degrees above the x-axis. So for an angle of 0, the height is 0, okay? When I ask you to graph this, that's the first point you plot, okay? Now for a 30-degree angle, keep in mind, I originally messed up my video because I put the radius in the wrong place. The radius is 12, okay? So that's 12. We've got a little 30, 60, 90 triangle right here, so I'm going to take out that 12 so I don't confuse people, okay? Based on the little 30, 60, 90 triangle, this length is 6, this length is 6 radical 3, okay? So that's technically the point 6 radical 3, comma 6, okay? I want the height of the point above the x-axis. So for a 30-degree angle, the height above the x-axis is going to be 6, okay? So on your graph, at 30 degrees, you're going to plot a distance above the axis of 6, okay? And you're going to continue with this tire moving. And by the way, this is symmetrical. So like over here for a 150-degree angle, that's also going to be, right, 150 over here, that's also going to be 12. You're also going to have a height of 6 and 6 radical 3 there. So 150 later in your table, you can go ahead and fill that one out. You're also going to have a height of 6 above the axis, okay? Let's continue for 45 here. And again, you may need to take some of these things out. You may leave them in, kind of depends on how neat your picture is. I'm going to take it out so we can really see what's going on in the diagram here. Okay, and so for a 45-degree angle, for example, again, the radius of the tire is still 12, okay? You would, for a 45-degree angle, you would be dividing by radical 2. 12 over radical 2 is the same thing as 6 radical 2. So you have a 6 radical 2, and you have a 6 radical 2, okay? So for a 45-degree angle, you're going to get a 6 radical 2. Now I'm going to ask you to plot this on a graph. You're going to need to convert this into a decimal form to be plotted on the graph. So, you know, putting the exact radical form is probably good just for practice purposes because you'll be able to do a lot of these things in your head. But for plotting this, that's about 8.49. Okay, so you can plot a point at about 8.5. okay? And you can continue. Now for a 60-degree angle, you're going to end up with the same triangle you had for the 30, just turned the other way. And so I think you'll end up with, the 6 radical 3 there for 60. And then you can get a decimal equivalent. At 90 degrees, it'll be at the point 012, okay? And so at 90 degrees, it will be 12 units above the graph. And then I gave you some graph paper to plot that. You know, we're not looking at every single possible angle, but I hope we're looking at enough angles that you can get kind of a general shape. Okay, and it's going to be a very distinctive shape, and I'm going to let you kind of toy around with that. If you need to talk to me on a live video, maybe tomorrow in the morning, well, actually you're probably watching this on Tuesday, aren't you? If you need to talk to me on Tuesday on video live, hopefully I can be available sometime that we can do that. But anyway, you should get a very distinctive looking graph happening. And so anyway, that's where we're headed with this circular functions investigation. Hopefully that gives you enough information that you can kind of figure out what's supposed to happen.